Good evening, folks. It's me again. Welcome to the interweb. Here we are again. We're doing this thing. I just want to catch us up a little bit on some of our lecture material. I want to finish up Chapter 8 and maybe start in a little bit on Chapter 9. Chapter 9 is pretty huge, so we need to get a jump on it, okay, before the end of the semester. So, all right, let's finish up here with this Chapter 8 business. Substitution versus elimination, basicity versus nucleophilicity. All right. And so here again, like I was saying in lecture, Klein loves to put stuff in boxes and make tables and stuff. And this is just one of his examples here where he wants to say these are nucleophiles only, and here's halides and sulfur nucleophiles, bases only. This is strong nucleophiles or strong bases, and weak nucleophiles or weak bases here. And these are things that he says that most likely react this way, but this is not, again, the only thing. Like you've seen that we've seen that nucleophiles like chlorine and bromine also act like bases when they abstract a proton after for example, like HCl undergoes like a protonation event. You can have chlorine come in and do some abstraction to deprotonate something if you have to. So this is just a rough idea about what these things act like. But these are not by any means the only way these things are employed, as you know. Okay, so again, be very wary about any boxes or tables. Okay, just in general, I will almost never use them personally, but if you want to use boxes or table, I recommend you generating your own boxes and tables, like and from your memory. If you can do that, that would be very helpful to get your own thoughts together. But don't just take someone's idea about what's categorized, as part and parcel of organic chem. Do your own thing, if that's how you think of it. Okay, it's helpful to sometimes see how other people do it, but if it's not helpful for you to put things in boxes or tables, or if it's tempting for you and you see it as a crutch, then just sort of ignore it. All right, and I'll go into why that is, because when you start putting things in boxes and tables, you make assumptions and about things that might not serve you well to make assumptions about. Okay. And so we talked about things that would be bases. Now, I would agree with this category, right, where you use hydride and DBN and DBU as bases only, because these are very specific reagents. Hydride is very small. We will learn the use of hydride very shortly, but not right now. But DBN and DBU are two other common amine bases, where we use the amine lone pairs here to their basic abilities. Okay, and these are used as just gigantically bulky bases. Okay, sort of like token toe, except maybe a little bit weaker there. Okay, and if you want to just see like a little example here you have DBN here acting to give you to pull off this external proton right here. Not that it has a choice, but it pulls off this proton right here, and this is this mechanism where this proton here gets pulled off by this pair of electrons on this nitrogen right here, and once that happens, this ends up being a resonance stabilized base. All right, so you end up making your olefin that you want to make, plus also here's your proton here that was right here. All right, and then this undergoes some resonance to be able to support that proton and trap that proton right there, which is actually pretty clever. Okay, DBN and DBU both have the same action. DBU is a little bit bulkier than that, and DBU is, in terms of industry, in terms of you working with it, DBU is the more popular reagent. Okay, the stronger the reagent, the more likely it is to promote SN2 or E2. Why is that? It's because it has more impetus. The SN2 has a stronger nucleophile, E2 is a stronger base. It generally speaking, even though hydroxide is happy having this oxygen have all these have all this extra electron density, it doesn't want to stay this way necessarily forever, right? This is a high energy intermediate. It wants to seek to neutralize or stabilize its charges too. So it always wants to go for another proton or another source of neutrality. Okay. So if it's a strong nucleophile, it will seek a carbon to be able to bond with, so it could share some electrons. If it is acting like a base, it will pull off a proton from somewhere. For example, here's your leaving group here, LG, to, to be able to quench that positive charge, giving you, your alkene plus your tert-butanol, and of course the hydrogen here being this hydrogen right there. Okay, so that's how that works out. So depending on what it is, all these reagents, as a strong nucleophile or as a strong base, seek the same thing. They want neutrality, either through protonation or through SN2 like Br, SN2 like reactivity. Here's your SN2 example right there. All right, it ends up here with Br minus plus CH3OH. Notice both of the resulting things are neutral. All right, these things are both now neutral. All right, so that's what we want to end up with. We want to end up with a neutrality. That's what their impetus is for wanting to do this. The weaker the reagent, the more likely it is for SN1 or E1Y, is because these things promote ionization of the electrophile, right? These guys here want to promote a carbocation formation. That's essentially why. All right, here's the stuff I really don't agree with at all, because this is great for you to do it and for you to derive all this for yourself, which you can, you totally can, but don't read this off of the textbook. I mean, it has a nice little summary section in the back of the chapter, but don't just read the back of the book and just say, well, here it is, and I'll just memorize this, because that is going to really sink you, okay? So don't do that. So be very careful about that. But here's saying, analyze the structure and analyze the function. So nucleophile only versus, for a primary versus a secondary versus a tertiary, it will give you, if it's a nucleophile only on a primary substrate, it'll give you primarily SN2. If it's tertiary, primarily SN1. But if it's a secondary, SN2, SN1. There's 4 of these slides. Okay, just go through them and see if they're helpful for you. But my suggestion for you is to go through each of the substrates and see if I have a strong nucleophile and I have a primary, secondary, or tertiary substrate, what would I get as a major product? And this is all that he did. He did the work for you, though. That's a bad thing. He shouldn't have done the work for you. You should do the work to derive this for yourself, because at this point right now, especially with your knowledge of E1, you have the knowledge to be able to do to generate these tables. Okay. Here's where it gets, this is sort of helpful, but here's where it gets like unhelpful. Yes, strong nucleophile versus strong base, great. Now we can do E2 or SN2, great. We know that. All right, and this is not always the case. This is not always the case for what this is. It depends on the substrate. So this is far too general. So if you really want to impress yourself, do this with a generalized primary, secondary, or tertiary just number, but then pick a real substrate and do it. You can do this. You can do, so what do you want to do here? So pick a substrate that would encompass both primary, secondary, and tertiary. Sure, you know how to do that. Let's give you a substrate right here. Right here is all that you would need. Here's your tertiary position, here's your secondary position, and here is your primary position, right? 2, 3. Now put your chlorine on your tertiary or your secondary or your primary and have at it with your strong nuke versus strong base. All right, and then do your own stuff. All right, rederive it for yourself. You don't need the book to tell you this. In fact, the book it's not bad, but it's doing the thinking for you, and you need to rederive it for your own brains. All right, and again, more ridiculousness here. Now with your primary, secondary, and tertiary for your weak stuff, your weak bases and your weak nucleophiles. Again, pretty not so wonderful, but do this for yourself, okay? Okay, and then predicting products here, the third point here on this summary slide is, again, for each of these SN2, SN1, E2, and E1, what you want to do is that you want to rederive, again, all your chemical and your stereochemical outcomes. You can read this here and make sure you understand it, but make sure that you know what this really is like for your own practical purposes. All right, that's the thing that you really want to do. All right, so I'm not going to read all this to you. You can read it yourself on the slides or in this video, but please feel free to rederive it yourself. All right, that's the thing that you really want to do. All right. All right, I think this is the end of this chapter right here. Let us zip on to chapter 9. We're just going to start chapter 9 here. We're not going to we're not going to go through the whole thing of it. It's just too important to just only do it by, hey, what are you doing? To just only do it by this thing here. But pen, pointer, pen color, blue. Because it's good to just do some examples, just generally speaking. Come on, blue. All right. But it's again very helpful to do it also live in class too. But we're running out of time, so. All right, addition reactions. This is huge. This is the real. Now we're just getting into the meat of this thing. Okay, addition is the opposite of elimination. All right. Notice if you want to do elimination, you are generating a series of alkenes. But let's just say we want to add stuff to these alkenes. Right? That's called addition reactions. Those are addition reactions right here. All right. And you have a lot of freedom as to what to add to these double bonds, and in so many different ways. This will carry you through the rest of this course, trust me. All right. So you want to add stuff to a double bond here, and how you're doing that, you're using the utility of a pi bond. All right. And a pi bond, which you're starting off with, either giving it to you in some problem, or you can generate it using some E1 or E2 reaction. Okay, so here's the addition of H and X, and H and O, and H and H, and again, here's a very generic substrate right here. Right, this is a 2,3 dimethyl butene here, and here's just showing you the addition of a hydrogen and a halide. Okay, let me just go back and erase this real quick. All right. And so how do you add the H and the X here? Well, no problem at all. We will show you that. But generally speaking, if it's an H and X or an H and OH, it might just be as simple as adding H. Let's say the X is a chlorine. It might just be HCl. That's as simple as that. Now, the addition of how they go on there, that's a different story. All right, we will go into that. All right. So here, a pi bond will often act as a Lewis base, or as a nucleophile, or as a Bronsted-Lowry base. All right, this is just showing you the different ways that a pi bond can act here. Okay, acting like a base here because a base is pulling a proton or yanking off a proton from somewhere. All right, that's how this is acting as a base. As a nucleophile, it is just going to be attacking some sort of electrophile. We'll see both of these examples in this chapter. Okay. So notice though, the action of the pi bond is the same. A pair of electrons is going from the pi bond and swinging up and grabbing something like a hydrogen here or some electrophile, right? And then that's being attached. This guy right here, was the former pi bond. This is the former pi bond, which is now a sigma bond. Because it swung out and grabbed that proton right here, or that electron right there, or that electrophile right there, that's why this bond is right here, because this is the former pi bond, and this carbocation right there, right, is left there because when this thing here swings out, imagine the swing open of a door. Imagine this is a door and you're swinging it open. All right, imagine it looks like this. Right, looks like this here, right, and imagine the pi bond here is a door swinging out. And let's just say this is some dweeb that you want to nail with the door. Wow, why am I anti-dweeb right now? That's normally I'm not that aggressive, but maybe, I don't know, maybe it's this beverage I'm drinking. Is it the beverage I'm drinking? I don't know. This is, why would lemon water make me aggressive? I have no idea. I'm gonna take some more lemon water. Oh God, that's good water. Anyway. This door swings open, nails that dweeb. Swing, nails that dweeb right there, okay? So the dweeb being nailed, right? Now we just draw the resulting thing. We now draw the open door attached to the said dweeb that we have nailed. That bond should be connected right there, all right? And then what you're left open with here is a carbocation, all right? Right there. Very messy, but that's what we're doing here, right? We're swinging this open. We're attaching this proton here to that former pi bond right there, and is resulting in a carbocation right there. That is the entire principle of this chapter. All right. So the addition here is the opposite of elimination. So from here you're adding HS. So here you can say you're adding HX across a double bond from here to here. But in another way, you can think of it this way. It's the reverse of the elimination, because the elimination, as you saw before, you took some base and you pulled off that proton there, that swung on out like so, and that swung on out like there, giving you the eliminated product, giving you this guy right there, right? And whatever that is, the base with the hydrogen on it, okay? But the addition is the opposite way of that, okay? And so this is a thermodynamic expression. We can assess the delta G, the free energy of the system, and be able to determine which side we can favor. We can actually manipulate the system so we can give us the exact product that we want. Okay, so typical addition reactions have a minus delta H. Why is that? Because most positive addition reactions here give off heat, and which is a negative delta H. Okay, and so normally that is the case. Normally these things are favored. If you have larger energy here at the very end here, you want to. This is something that will give you the positive thermodynamic profile. You are generating some energy right here, which is going to drive the reaction this way. All right. So that's what you want to do. So you're having bonds broken versus bonds formed there, okay? And so how we normally determine the sides, which way to determine, which way to go in terms of thermodynamic equilibria, we want to be able to add or subtract heat from the entire system to go either to the right or to the left, okay? And so there's a few different things. There's the enthalpy term, which is the thing that we really care about. And then there's the entropic term here. The entropic term is a very interesting term. We normally don't use it that much, but it's good to describe the system. But we really don't normally do this kind of thing, okay? But what it is good for, it is good to show us that we can increase entropy in the system using certain temperature profiles, right? And using certain concentrations here, okay? But to favor addition, a minus delta G or a positive delta entropy is totally needed, okay? And so that's to favor that's to favor the addition, okay? And so what does that mean? That means that we have a total loss of not a total loss, but a increased loss of entropy, right? We are if we're favoring addition, we're having more order in the system, all right? To favor elimination, we have the reverse, okay? So we have things that are leaving, and so we are increasing entropy in the system, okay? And so, but that's great to know and to talk about, but really the thing that we really care about is temperature. Temperature here is the thing that is the most important thing. If we want to favor elimination, we want to add heat. If we want to favor addition, we want to add cold, all right? So make the reaction cold, all right? That's sort of the thing that we had talked about before with SN1, SN2 versus E1 and E2, okay? Note the temperature used in this reaction, okay? So if I'm adding HBr across a double bond here, right, and it is going to give us this bromide right there. Let me just point out to you that this hydrogen right here is not. So here's the original hydrogen, right? This is the one that was already here, right? And here is the original hydrogen that is still going to be there. But this new hydrogen, let me just circle it. This hydrogen here that we just added here is this one right there. And this bromine right here is, of course, this bromine right there. Okay? So that's how that goes. All right? And so this is a typical addition reaction of a binary acid across a double bond, okay? And again, it's favored by the cold conditions. Doesn't matter whether the Br adds to the right side or to the right side of the double bond or to the left. Does that matter here? In this case here, it does not, because why? This is a symmetrical molecule. So it doesn't matter if it adds to the right or to the left. It doesn't really matter at all. It will matter though. It will totally matter. All right, let me take a break right now, and I will come back and finish up the rest of this lecture, probably about another half an hour, 45 minutes or so. Thanks for your attention, Internet. Bye-bye.